All right. Well, it says it's recording, so I am going to assume it's recording. Excellent. All right, guys. We have today our last main trig function. This is the tangent function. And you know what? We don't have to see that written out, so let's just write it out here. Tangent function. And if you go on to higher math, you get into like calculus, there's something called the tangent as well. And it's not quite what we're talking about right now, okay? So, or even in geometry, you know, we're talking about a tangent line. No, this is our tangent function, one of our trig functions. And the tangent function is a combination of sine and cosine. It's a combination. Look, sine of theta over the cosine of theta. That's what the tangent function is. So in essence, I mean, the tangent function looks really different than the cosine and the sine function, but we already know a little bit about the sine and the cosine function. Remember when we were paying attention to the sine function as it goes around the unit circle, we were looking at the y values. When we were looking at the cosine function, that was the x values, right? So in essence, if we're given a theta value, which we're going to fill in this table, we know what the sine of these values is going to be by looking at the unit circle. We know what the cosine of theta is going to be looking at the x values in the unit circle. And all the tangent is going to be is divide the y value, the sine of theta, divided by the cosine of theta. Okay? So if you didn't quite get that, I mean, that's verbal explanation. Let's go ahead and work it out a little bit. So look on the screen here. We're going to do all of the sine functions for our 4 values here. And remember, the sine function is looking at the y values along the unit circle as we rotate a certain number of radians around the unit circle. So if I'm here at 0 radians, 0 degrees, how far up and down am I? How far up and down? I am at 0 for y. I can also look at the ordered pair that's given here. So I know that, I'll do it in different colors for you. I know that the sine of 0 is 0, okay? Because again, the sine is connected with our y values on the unit circle. So at 0 radians, the y value is 0. All right, how about when we rotate, I'm gonna draw a little unit circle over here too so I can kind of reference it clearly. So here is 0, we have pi over 2 at the top, we have pi, we have 3 pi over 2, and we get all the way around, we're at 2 pi. So if I rotate it around here, y value is 0, but if I rotate around, what's the y value here at pi over 2? It's up 1, because this is a unit circle. It's 1 and all radii is 1. So at pi over 2 for sine, I end up with 1. Okay. And as I rotate around, I get past pi over 2, I keep going, I get down to pi. What is the y value? That's up and down, remember. What is the y value here at pi? You could see from the unit circle, it is 0. 1, 0, 1, or 0, 1, 0. Oh, binary. Okay, now let's keep rotating around. Get all the way to 3 pi over 2. I'm down 1. The y value is down here. It's 0, negative 1. The y value is negative 1. So I'm going to put in here negative 1. Oh, that's how you do it. Yes. Okay. Lastly, if I rotate all the way around 2 pi radians, I get all the way here, and I am on the x-axis, which tells me my y value is 0. It's always going to be the same. These are the same. These are the same. Okay, make a little arrow from 0 to 2 pi. That's the same location that's rotating all the way around. We end up at the same point. It's like this right here is like a car going around a track. Get back to the start. Get back to the start. So 0, 2 pi, 4 pi, 6 pi, 8 pi, 10 pi. It's always that distance all the way around. All right, let's do it for cosine a little quicker this time. We could just look at the unit circle. So looking at the unit circle over here, looking for the x values as we go around now because we're assessing cosine. And we're going to end up with, I wish this had green. It doesn't. Okay, when we're right here at 0, we're at 1. 1 for x. At 0 radians, the x value is 1. At pi over 2 radians, the x value is 0. As we rotate around, we get over here to pi. That's at -1 for x. We keep going around. 3 pi over 2 is at 0 for x. And we already know once we get all the way around, we're over 1 again. And we already know that 0 and 2 pi are going to have the same measurements for everything because it's the same radian location. Okay. So now what we need to do is we just need to make our fractions because look, the tangent of theta is the sine over the cosine. The sine over the cosine of theta. And it's going to be the same theta we're assessing because here the theta was 0, the sine was 0, the cosine was 1. So guess what? The tangent is 0 over 1, 0. You see, so we did the work with cosine and sine. The tangent is equal to the sine over the cosine, sine over the cosine. So we put sine over the cosine, 0 over 1. That's equal to 0. My next question for you is for those who like to make cookies, because would you like one of my 0 cookies? Who wants 1 out of 0 cookies? I think this is hilarious. I don't know why no one's laughing. Hey, I brought cookies. How many? Can I have one? Yeah, you can have 1 out of my 0 cookies. Man, that's like the worst thing you could do. That is undefined. We can't even define that joke. Is it good? Is it bad? It's neither. It's moot. Blah, blah, blah. All right, here we go. Now we're at pi radians. Pi radians. 0 for sine, 0 for y. -1 for cosine, our x value. 0 over -1. 0 over -1. It doesn't matter that it's 0. That's -1. It's still going to be 0. Now, you might even like this joke better. Would you like -1 out of my 0 cookies? Who wants -1 cookies first off? If someone offers you -1 cookie, even if it's out of 0, just say, get out of here with me. Get out of here. All right, look, anything over 0 is undefined. We're going to have an undefined again. Somehow that joke got worse. Lastly, 0 over 1 is 0. And you know what? It's always going to be the same. Anytime you have 0 and you have 2 pi or 4 pi or 6 pi, 8 pi, 10 pi, 12 pi, you're always going to end up with the same values, the same everything because it's the same location on the unit circle. All right. That was the first step to see how tangent works. Okay, it's all based on remembering sine is related to the x values in our unit circle. Sine is the y values in the unit circle. Cosine is the x values, are the x values. So we use what we know about sine and cosine. The tangent is always just a combination. You can't go to the unit circle and spot and see what the tangent is. It's like this is just like a deeper level. You can go and see what these are, but then you have to combine them to get over here to see what the tangent is. Okay, so it's just like a deeper level. The tangent is just at a deeper level. All right, now we're going to go down here. We're going to play around with this guy because we have a very similar equation to what we were using before. Somebody tell me what's different. First off, I'm being a little better. Some books you'll have it expresses x, some as theta, so I wanted to just show that they're the same thing. That's not what's different between these two things. Everything else is, there's a lot of similarities. So this is different, that's true, but what else is different? What else is different? Between our tangent, really that's the tangent function, the parent function ready to be transformed, and we have the cosine function ready to be transformed, moving up and down, side to side, all that. But what is different between the tangent equation and my cosine equation? What's one thing that's different? What do you see? A. Tangent cosine, yeah, we knew that'd be different. B, theta and x, they're synonymous. I just put it there to show the difference. Oh, look at that. There it is. One is plus c, the other's minus c. Tangent is getting all something funny. Tangent is, it didn't come in. Tangent's different, just wanted to be different. It has plus c instead of minus c. That's the only difference. So if we spot in here that it's, plus pi, we know c value is pi. Where here, if we had this and this changed it to be x plus pi, we would know that that had to be a negative pi to make that happen. Here, we just got to keep that in mind. That's the only real difference. I'm done with that. Okay. Now, let's look at this, because up here, we did some of the work to see what tangent of theta looks like. What tangent of theta looks like, okay? Because essentially, remember that the tangent function is going to fit on this equation. Our parent function is going to fit here. And I've already put 2 of my radian measures along the x-axis here that are going to be really important. Because I look up here and what happens at these radian measures? What happens at pi over 2? Bad joke. What happens at 3 pi over 2? A joke you wish your teacher would never say again. Sorry. Every year. You could probably watch a video from 2 years ago. I'm saying the exact same thing, trying to make it funny, trying to make you guys laugh a little bit. And I don't even care if it works. I'm entertaining myself. So what we're going to put here, and this is something kind of new, because I know that at pi over 2 for the tangent of x, it's what I just figured out. Tangent of theta, tangent of x, same thing. Assessing different thetas here. I know that whoa, one sec. Yeah, that's fine. I know that at pi over 2, okay, it's undefined. That is actually not a dashed boundary line like we were doing before. This is an asymptote. ASY. An asymptote is like an invisible boundary where something's undefined. The function cannot go through that value. It's undefined at that value. Okay? And what we're going to see is that it's undefined at pi over 2. And if I went in here and I want you to add a theta real quick. Let's add negative pi over 2 because I actually set this up a little bit less than perfect, which is fine. We're okay with being imperfect. At negative pi over 2, right, that's going down. I end up with negative 1. Go ahead and just input these values for me as well. I end up with 0. And I end up with negative 1 over 0, which is undefined. So what I did is I basically I did this for negative pi over 2. And I'm going to see that it's exactly the same values as 3 pi over 2. Because look what I did. I went negative pi over 2. Instead of going positive pi over 2, I went negative. And that's the exact same point as 3 pi over 2. I just went in the negative direction. And I really should have done that beforehand. In fact, if you're highlighting or doing something like that, highlight this first one because that's really what I wanted to show you. So we know that the asymptotes are going to be at pi over 2. They're also going to be here at negative pi over 2. That's another asymptote. ASYM. Okay. And this is the parent function. Remember that up here I was assessing sine and cosine to show what the tangent is, the tangent of theta. And that's what I'm graphing down here. I'm graphing my parent function of just regular old y is equal tangent of theta. Now I know that we have these asymptotes because based on the theta value, which I'm expressing the radians along this x values here, that's where they're undefined. So I have to put the asymptotes there first. But honestly, guys, once you get the asymptote, you're getting close. You're ready to go. Let's put in a couple more points. What's happening at 0? Let's see. Theta is equal to 0. the tangent of 0 is just the sine of 0 over the cosine of 0, right? Because remember, the tangent is just sine of whatever same angle I'm looking at, sine of theta over cosine of theta. So the tangent of 0 is 0 divided by 1. 0 divided by 1. The tangent of 0 is 0. Okay, so watch. Here's our first point. That's our main point. That's our main point. I put this here. The parent function always goes through the origin. We're moving it around and up from there. But the exact same shape, maybe with a little bit of compression or not, but the same shape is going to be moved over. It's going to be moved up, right? If this was the tangent of theta plus 1, I'd put the point at plus 1 because it would just move up, okay? So think about it as a parent function that we're manipulating to move around, move up, squish it, or compress it, squeeze it, stretch it, all these bop it, pull it. Just kidding. Let's go with what's next. Let's look to see what is happening to this function at pi over 4. Let's do this one. It's at pi over 4. Okay. So if I was adding that, maybe I want to add it to my table. If you just don't have the room for it, you can add it at the bottom of the table. But if I added pi over 4 to this, right? Looking at pi over 4, the sine of pi over 4 is root 2 over 2. The cosine of pi over 4 is root 2 over 2. And root 2 over 2 divided by root 2 over 2, root 2 over 2 divided by root 2 over 2, it's the same thing. So it's equal to 1. So watch. When we go here to pi over 4, we're going to end up at positive 1. If I went and did it at negative pi over 4, I would end up at negative 1. And I just want you to know what's happening on the right side of the graph because the same thing happens on the other side. It's symmetric. So I don't need to add negative pi over 4 to my table because watch what we're going to have now. We're going to have, it doesn't go and touch the asymptote, but it comes close to it. It goes down through the origin, down through the other point, and then it goes and it doesn't touch the other asymptote. It just keeps going down right next to it, just like an exponential equation. That's the tangent function. It's a little more curvy than that. We'll do another. Okay. So that's our parent function. That's our parent function. And we're always just moving it around from there. We're moving it up, down, left, right. Yeah. All right. So next, take a look with me over here. Okay. I had the same function here, all set up for us, and we could see that a is 1. So a is 1 is just tangent of, b is 1, so it's just tangent of x. C is 0, so it's still just tangent of x. D is 0, so really this is just tangent of x. I have all these sliders set up so that they're perfectly, this is just showing the tangent of x. Okay. Now, if I look at the graph here, I could pull out some points, and I see that at pi over 2, right here, I'm at 1. Down here at at pi over 4, I'm up here at 1. At negative pi over 4, I'm down here at negative 1. I could see that my asymptote is at negative pi over 2 and positive pi over 2. Okay. And now let's see what happens when I manipulate some of these things. Okay. So let's manipulate a. Let's, instead of it being positive 1, let's make it negative 1. Watch what happens. Exactly flipped. You see how that exactly flips? It's just like if I had, if I just had y is equal to x squared, right? But then if I make it negative, right, what happens? It switches down. Positive, negative, positive, negative, positive. So it's the same idea for all functions. They just flip. Anytime you have the negative version of the function, it just flips. So that's negative 1 for a. Now let's go all the way back. Let's put it back a positive 1. And now we're back to our we're back to like y is equal to the tangent of x. Now we're just at the parent function again. Let's manipulate something else. Let's manipulate our b value, see what happens with b. If I manipulate my b value, make it bigger, what's happening? I'm gonna get rid of these lines right here. These are my asymptotes that aren't shifting with me. But look, if I have my b value, whoa. It's kind of like frequency, right? It's kind of like frequency, but actually the frequency of this, let's put it at 2, and maybe we can make a deduction here. If I put it at 2, what I'm noticing is between 0 and pi, I could see that there's, half going up, there's a whole one here, and then there's a half going up. So between 0 and pi, there's 2. That's the difference with tangent. We'll talk about it more, but I want you to keep in mind that the b is synonymous with frequency, but instead with tangent, it's always over a pi. Look at the notes right here. This is where that comes in. Instead of it being 2 pi divided by the frequency, with tangent, it's only pi divided by the frequency. And that has to do with what we were talking up here. This is really hard to conceptualize why that is only pi, but it has to do with these ratios. Remembering tangent is the combination of two different functions. Tangent is hard, guys. We might spend 2 days on it. All right. Okay, so I'm going to put b back to 1. Now we're back to our regular. And now let's do c. Tell me what happens here, or think about it. Watch. Oh, you're getting sleepy. Move it this way. Right? All we're doing, like I'll play it. All we're doing is moving it left to right. I'm getting dizzy. Let's stop that. We're just moving it left to right. This is our horizontal shift. So look, if I go to this and I shift it, let's shift it 3.14 because these are in radian measures. I'm just doing 3.14. Hello. If I did it like this, look what happened. The movement was through the origin, and I moved it all the way to 3.14. I can actually put it in as, let's do this. Let's put it in as pi over 2. You see, instead of it being at the origin, it moves over to pi over 2. Instead of tracking the starting point, like with sine and cosine, we're finding this inflection point right here. That's what's moving with our horizontal shifts. So let's get rid of this. Add a slider, get it back in there. All right, that's a lot of mess. All right, get up there. All right, but now we're back to where we started. Let's put it back. Ugh, get over there. Okay, I'm gonna let you use Desmos to double check yourself, guys. You can use Desmos. Okay, so graph it first on your own, get as far as you can, then double check. And then look, the last thing is, remember, always looking at this inflection point of 0, 0. That's always like where we're looking at. We're gonna have one asymptote on the left, one asymptote on the right. And when we deal with the d value, all it does is move it up, move it down. Okay? It's the same aspects, it's just slightly different shape that we're manipulating. And there is more to it. You'll learn more about this. There is more to it. Maybe we'll split this up and do the second half on Thursday. Okay, but that is what we have as far as what these different things do. Okay, so let's try to do, let's see, it's 2:30. Yeah, we're going to do like probably 2 examples. We'll get 2 examples in, and I'm going to bring in the unit circle again. And let's go ahead and get out another piece of graph paper if you don't have it. We're going to do this example right here, and we're going to be comparing it to the tangent function. So maybe I should even just keep that there. Let's keep it. All right, we'll keep the tangent function up here. All right, there's our tangent function. Whoa, why is it not? Oh, that's why. Good. All right, let's look over here now on the doc cam, and we're going to be graphing our first example here, and that is y is equal to the tangent of 2x. Okay, so first off, I need to go in here and remind you now, this might be better to share this now. These have no amplitude. it's not like, so remember with sine and cosine, there was an amplitude, right? There was an amplitude, like the top of the roller coaster, the bottom, right? There's no way to show an amplitude with the with the tangent function, because it's not as if there's a top and bottom. There's only going to be this repeating pattern. It repeats and it repeats, and there's dashed asymptotes between them, dividing them. So there's no amplitude. The A value we're going to think about right now as if the A is negative, it flips it. I showed you that. It does some other things, but we'll keep it at that for now. To find the period, which is the length of each of our repeats, right? The length of each of our repeats, we take pi and divide it by b. Horizontal shift is a little more complex. We'll get to that. The d value is moving up and down, right? Vertical shift. So let's see what we have here. We may not have all these aspects, but let's pull them out. A is positive 1. Go ahead and write it down. A is positive 1. How do I know that? A is found out here, and A is positive 1. Okay. What's our B value? B, look where it is. It's like a map. It's right in front of theta, or in this case, we call it x. So B is 2. Okay. C is 0. Right? There's no like theta plus 4. There's no like 2x plus pi. It's not in there. And D is 0 as well, because that's plus 0. Okay. So, well, there's a plus 0 in here too. I guess I could put in there. Why not? So we have A, we have B, we have C, we have D. Okay. We already have a lot of information. We actually have a lot already, because we know that it's not flipped. It was positive. We know that there's going to be there's going to be like a frequency. There's going to be 2 repeats within pi, right? So to find the period, we take our B value just like we took the frequency before, and the period is going to be pi divided by 2. That tells me that each repeat is going to happen within a period of pi over 2. Instead of before, look how long the repeat was. The repeat was in the standard tangent of theta. The standard repeat is over a distance of pi. Negative pi over 2 to pi over 2 is pi. Okay. So we know that the period is slightly different. We know there's no horizontal shift. So no horizontal shift. There's no vertical shift up and down, left and right, up and down. There's none of that going on. We know that it's not flipped, right? So I look at this. There's no horizontal or vertical shift. That's nice, because that is going to allow me. Now we can cover that a little bit. That's going to allow me to see that. Let's put our graph together here. That, let's say, let me see, do that like that. It's going to be like that. That's going to be, yeah, let's do that here. So spread it out a little bit. There's pi over 2. So this is pi. Go 4 over negative pi over 2. Go over a little bit more, pi. Negative. So look, remember on the left side of the screen, that has tangent of x. That's just our regular parent function. We know that the parent function goes through 0, 0 if there's no horizontal or vertical shift, right? So look, if there was a vertical shift, look where it goes, right? It goes up, because the whole inflection point there at 0, 0 is moving up. But since we have no horizontal shift, no vertical shift, we end up with, get over there. We end up with our same asymptotes that we have in the parent function. So go ahead and put those. Okay. All right, now we have to look a little closer. We see that one sec, let me do some real quick. 0 tangent 0, 0, 0. Yes. Come over there. Oh, one sec, hold up. No horizontal shift. Doubles it up. Sometimes it's helpful to see where you're going. Let's see what's happening here. Okay, that's still going through there. Right, gotcha. Okay. Okay. 1 sec. Just give me a moment. No. I am going to start this problem over. We're going to start it over on Thursday because I am psychically feeling that all of our brains are pretty full right now. Guys, in the chat, we did the parent function. I think I might actually stop with that and wait to get to a little bit deeper on Thursday. Okay. Now, just in the chat, everything we've talked about so far on this page, go ahead and give me in the chat on a scale from 1 to 5 how we feeling so far. Actually, I really like this feedback, please. Good. 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 Okay. Okay. Good. There's a kinking in there. Okay. That's why. That's why. Okay. Then, honestly, I kind of I got minorly confused here. What we're going to do is, I do want to finish this problem, and then we're not going to have to do the homework tonight. We'll look at it after we get through the second half of this lesson. I just would like to break it into parts. So I need you to either get rid of those asymptotes or start a new graph, just like that. Okay? Because one thing that I misled right here is based on the period, based on how wide, right? How wide this tangent looks, based on how wide it is, that also dictates where our asymptotes are going to be. So just because it didn't move up or side to side, it's still right. The asymptotes are going to be based on how wide the tangent function is. How wide it is based on the frequency of 2, the period, which is pi divided by the frequency, pi divided by 2. So since that's the case, we are going to note that these two things occurred. All right, I'm back on track now. We are going to account for that. Those two things occurred. So we know without any horizontal or vertical shift, it still goes through the origin. So everybody go ahead and start with that. That's where we're going to start. Step 1 is find where that inflection point is. In relation to what? In relation to where it is in the parent function. Okay, so it's always at 0, 0. And since we didn't have any vertical or horizontal shift, it's still going to go through there. It's still going to go right through the origin. Okay. Now this is where we need to keep in mind, and we'll do more complicated versions on Thursday, and I may even supplement what I'm showing off right here. But I know that my period is pi over 2. Pi over 2, right? So what that is saying is, here's the inflection point. Here's like the inflection point right here, right? But pi over 2 is how wide it is, right? So that's not meaning that I go pi over 2 here and pi over 2 here. It's saying from that inflection point, we go out pi over 2. So as far as if I end up that far out, that would mean that the distance between the fingers are pi over 2, you see? So the period is going to be from this inflection point, our starting point, and we're going to go from that starting point out so that the distance between my fingers here is pi over 2, and that's where our dashed lines are going to be our asymptotes. So look, if I go to the left, negative pi over 4, I go to the right, pi over 4, right? That distance between those two things, between those two values, is pi over 2. So you look to see the period. First you look, is there a horizontal vertical shift? That helps you find the inflection point. Inflection just means where it kind of changes the direction and curvature. So I go find the inflection point. My period is pi over 2, so I need to go out so that the distance between is equal to the period. And that is where I'm going to put my dashed lines. Okay. And this is where there's going to be more details I can add to this for Thursday, and I'm glad I've decided to break this up because we look at the a value of 1. That means it's very standard. It's just the y is equal to the tangent of 2x. The a value has a little bit to do with how compressed or stretched out it is. That's getting to a whole nother level. We'll hit on that on Thursday. But what I'm going to point out here is we know the shape of this graph. We know this is the center point. And what we're going to do is for today, Thursday we'll get a little more refined with this. I'm going to go ahead and make my graph between the two asymptotes. And then if you go another same distance here in either direction, you're going to get another repeat. And then deja vu. You go to the left, you make your asymptotes. You're going to get the same thing. So there's really only a couple aspects to this. There's, in relation to the parent function starting at the origin, we're either moving this point up or to the side in either direction, right? We know that based on the period length, we go from that starting point, the inflection point, and we are making sure that the width of one of our functions is equal to the period length, right? And we are paying attention if it's positive or negative. Here it's positive, so we know it's not flipped. So actually the tangent kind of popped out pretty quick for this one. That's done for that problem. Yeah, I got a little turned around there, but we're gonna pause and continue this lesson on Thursday. So you don't have homework for this, just because I think it's better for us to take a little bit more time on it. Okay, and hopefully that supports you guys too, getting some other things done. All right. Give me thumbs up, sideways, down. Thumbs up, sideways, down. What do you think? We're gonna yeah, that's what I expect. We're gonna get a little bit further with this. It wasn't bad there with the check-ins. We're at about a 4 out of 5 or so. So allow this to sink in. Allow the main thing to remember, just kind of summarizing, is the tangent is the sine over the cosine, right? There are undefined aspects because we have a fraction, and a 1 out of 0 cookies is undefined. It's mean, so that's where we get the asymptotes. Okay. It has the plus, that's slightly different. We know that we're looking at the period over a interval of pi instead of 2 pi compared to the other functions. So once we know the period, we go from the inflection point out. And the only difference for the location of the inflection point is if there was a vertical shift or a horizontal shift, which is what we're going to talk about on Thursday because we didn't get to it. That's all we did. Whew. Made it. All right, let me stop this video.